It begins in the dim glow of oil lamps, in lecture halls smelling faintly of chalk and ink, at the closing years of the 19th century. Europe hums with the confidence of reason. Steam engines thunder through valleys. Telegraphs hum along copper veins stretched across continents. And the great physicists of the age believe that nature has nearly surrendered her final secrets. Newton's laws reign supreme. Maxwell's equations have tamed the lightning into mathematics. The atom, that invisible grain of existence, is imagined as indivisible, eternal, and obedient to predictable rules. The universe seems a grand clockwork, its gears turning in measurable harmony, each tooth of cause yielding its effect with exquisite precision. And then, as though the cosmos itself chose to whisper rebellion, a problem arises in the glow of a furnace. In Berlin, 1900, Max Planck stands before a black body, a metal cavity heated until it glows, and wonders why the mathematics of classical physics refuse to describe the spectrum of its light. The equations break, yielding nonsense at high frequencies. Energy, according to the rules of Newton and Maxwell, should flow continuously, smoothly, like a stream. Yet experiments insist on something else, something jagged and strange. The energy emitted seems to arrive in discrete bursts. Planck, hesitant, almost embarrassed, introduces a desperate assumption. He imagines energy not as a continuous quantity, but as small, indivisible packets, each one a quantum proportional to the frequency of its light. It is an act of mathematical rescue, not revelation, or so he believes. But this single step, this quiet hypothesis, cracks the marble temple of classical certainty. The 20th century begins not with wars or revolutions, but with the smallest act of disbelief. A man daring to say that energy itself comes in pieces. Planck's formula works. The experimental data fits perfectly, as though nature herself had been waiting for this word, quantum. But Planck himself remains skeptical. He treats his discovery as a trick of calculation, not as a window into reality. Yet far to the west, a young patent clerk in Bern will read Planck's paper and see in it not a trick, but a door. Einstein, restless, uncredentialed, surrounded by the ticking of clocks and the hum of bureaucratic precision, finds in 1905 the courage to take Planck's idea literally. Light is not merely a wave rippling through ether, but a stream of photons, particles, each carrying a quantum of energy. It is a scandalous thought. The wave theory of light, cemented by centuries of experiment, stands like a cathedral of reason. But Einstein is not deterred. To explain the photoelectric effect, the way light can knock electrons out of metal surfaces, he insists that only by accepting light as particulate can the phenomenon make sense. In his mind, the duality begins. Light is both continuous and discrete, both wave and particle, a contradiction so elegant it will haunt physics forever. The world does not immediately follow Einstein. The idea of quantized light is too wild, too alien. But as the years pass, experiment after experiment begins to yield under this new logic. Niels Bohr, in Copenhagen, a man of strict self-discipline, and almost poetic intensity, finds in 1913 that the atom itself seems to echo Planck's quanta. Electrons, those ghostly travelers circling nuclei, do not move along smooth orbits as planets around the sun. They leap between distinct energy levels, emitting or absorbing photons as they do. The atom becomes a staircase of energy, not a ramp. It is a model that dares to combine the mechanics of the heavens with the discontinuities of the unseen. Bohr's atom, painted in textbooks as neat circles with jumping dots, hides a deeper truth. It is a compromise, a bridge between the classical and the quantum. It works, but no one yet knows why. Bohr himself feels the fragility of the model. He senses that something fundamental is missing, a new logic, perhaps, or a new kind of mathematics. In Göttingen, in the feverish intellectual air of the early 1920s, a generation of young physicists rises to confront this mystery. Werner Heisenberg, 23, restless and meticulous, plagued by hay fever and doubt, decides one sleepless night on the island of Helgoland to abandon the idea of electron orbits altogether. Instead, he focuses on what can actually be measured, the frequencies and intensities of light emitted by atoms. Out of this ascetic devotion to observables, he builds a new mathematical language, matrix mechanics. It is a wild departure, reality described not by smooth curves of position and velocity, but by grids of numbers that encode probabilities, transitions, and uncertainties. Bohr sees in Heisenberg's work the dawn of a new era. Einstein, though, frowns. The young are rewriting the laws he helped found. Meanwhile, in Zurich, another mind approaches the same problem from a different direction. Schrödinger, elegant, cultured, disillusioned by the mechanistic dryness of matrices, envisions instead a universe of waves. He imagines the electron not as a point, but as a wave of probability, spread in space, guided by a mathematical function, the wave function. In a burst of creative clarity during the winter of 1925 to 1926, he writes the equation that bears his name. The Schrödinger equation hums with a strange beauty. It describes how these waves evolve, how their crests and troughs encode the likelihood of finding a particle here or there. It restores, at least on paper, the continuity that Planck had fractured, and it reveals a new world of harmonies hidden within the atom. The orbits of Bohr become standing waves. The quantum jumps become resonant transitions. The two theories, Heisenberg's matrices and Schrödinger's waves, seem utterly different, yet within a year they are shown to be the same story told in two languages. The mathematics of uncertainty and the music of wave functions merge into a single vision, quantum mechanics.
Yet even as this triumph unfolds, comprehension lags behind discovery. What, after all, is real in this new world? Is the electron a wave or a particle? Does it exist in one place or many? Heisenberg, pursuing this question to its logical edge, writes in 1927 his principle of uncertainty. One cannot know both position and momentum exactly. The more precisely one measures one, the more blurred the other becomes. Nature, it seems, refuses to reveal all her cards at once.
Bohr interprets this not as a limitation of knowledge, but as a feature of reality itself. He formulates the principle of complementarity. The wave and particle pictures are not contradictions, but complementary aspects of the same truth. Measurement, he insists, is not passive observation, but active participation. The observer and the observed are inseparable. This view, soon called the Copenhagen interpretation, becomes the philosophical backbone of quantum mechanics. It suggests that the act of measurement collapses the wave function, forcing potentiality into actuality. A system exists in many possible states until observed, and the observer's inquiry determines which state manifests. The world is no longer a detached machine. It is an interplay of probability, observation, and existence. Einstein cannot accept this. To him, the notion that God plays dice with the universe is intolerable. He exchanges decades of letters and debates with Bohr, challenging the indeterminism at the heart of quantum mechanics. Their arguments, sometimes gentle, sometimes fierce, become the theater of 20th century thought. Bohr, patient and paradoxical, answers Einstein's thought experiments with deeper paradoxes still. At the 1927 Solvay Conference, the great minds of physics, Planck, Einstein, Bohr, Heisenberg, Schrödinger, de Broglie, and others, gather in a single room. Photographs of that meeting have since become icons of an age when intellect bent space itself. There, amidst cigar smoke and chalk dust, the old world of certainty finally yields to the new. The double-slit experiment stands as the ultimate emblem of this revolution. When light, or electrons, are fired through two slits, they form on a screen not two bands, but an interference pattern, as though each particle passed through both slits simultaneously and interfered with itself. But when one attempts to observe which slit it goes through, the interference disappears. The pattern collapses into two simple stripes. The universe, it seems, behaves differently when watched. Consciousness, or at least measurement, enters the equations of being. Yet even as philosophy swirls, the practical power of the new physics grows. Quantum mechanics explains the stability of atoms, the chemistry of bonds, the spectra of stars. It gives birth to solid-state physics, to semiconductors, to the lasers and transistors that will reshape civilization. The equations are mercilessly abstract, yet their predictions align with experiment to uncanny precision. Nature speaks quantum fluently.
even if humans only begin to stammer. In 1928, Paul Dirac, quiet and austere, extends Schrödinger's equation to include the principles of special relativity. Out of his mathematics leaps an astonishment, the existence of antimatter. For every particle, there must be a mirror twin of opposite charge. When matter and antimatter meet, they annihilate in a burst of pure energy. Dirac's equation unites quantum mechanics and relativity in a single elegant gesture. Within a few years, the positron, the electron's antiparticle, is discovered experimentally, confirming Dirac's dreamlike prediction. The quantum realm is not merely strange, it is fertile, birthing realities unimagined.
As Europe darkens in the 1930s, quantum theory migrates with its thinkers. Born in universities and cafes, it crosses oceans in the minds of refugees fleeing totalitarianism. In the United States, at Princeton and Berkeley, the new physics flourishes. The quantum understanding of matter begins to merge with nuclear physics. Inside the atom's nucleus, protons and neutrons dance to quantum rules of their own, bound by forces far stronger than electromagnetism. To describe them, a new quantum language arises: quantum field theory. Here, particles are not objects, but excitations of underlying fields, ripples in invisible oceans pervading space. The electron is a vibration in the electron field, the photon a tremor in the electromagnetic field. The vacuum itself is alive, a sea of potentiality, seething with virtual particles that flicker into existence and vanish in the blink of a mathematical eye. Quantum electrodynamics, QED, emerges in the post-war years as the most precise theory ever built by human thought. Richard Feynman, with his impish humor and sketches of wiggly lines, invents the diagrams that bear his name. They become the hieroglyphics of the quantum world, showing how particles interact, merge, and scatter. Every electron-photon dance can be drawn, calculated, and compared with experiment to extraordinary accuracy. The anomalous magnetic moment of the electron, predicted by QED, matches measurement to better than 1 part in a trillion. Never before has human reason mirrored reality so perfectly. Yet, as the equations grow in success, understanding retreats into paradox once more. The quantum vacuum predicts infinities. Renormalization tames them, but at a philosophical cost. What does it mean that every calculation requires subtracting infinities to yield finite results? Feynman shrugs. The method works. The universe, it seems, forgives mathematical heresies if they yield truth. By mid-century, the quantum vision has reshaped not only physics, but philosophy, art, and literature. The indeterminacy of Heisenberg and the complementarity of Bohr echo in the brushstrokes of abstract painters and the verses of modernist poets. The certainty of Victorian science dissolves into probability. The observer is no longer outside the experiment, but part of it. Human consciousness itself becomes suspect. If observation collapses the wave function, what role does the mind play in reality? Some see mysticism, others madness. The physicists, weary of metaphysics, turn back to their instruments. Quantum mechanics may defy common sense, but it builds lasers, transistors, atomic clocks, and soon computers. The practical triumph silences doubt. The world runs on quantum. And yet, beneath the hum of success, a deeper unease begins to ripple through the fraternity of physicists. The equations work, yes, but what do they mean? What is this quantum wave function that whispers the probabilities of existence? Does it describe something real, or merely encode our knowledge? The Copenhagen school holds firm. Reality is what can be observed, nothing more. But others, restless, refuse such modesty. Among them is Albert Einstein, older now, slower, but still defiant. With Boris Podolsky and Nathan Rosen, he crafts in 1935 a paper that will echo across the decades, the EPR paradox. They imagine two particles that interact and then fly apart, their properties correlated. Measure one and you instantly know the other, no matter how far away it is. To Einstein, this suggests that quantum mechanics is incomplete, that hidden variables must lurk beneath, carrying the full information of reality. To Bohr, it is proof of quantum wholeness, the inseparability of the universe. Between them lies not merely disagreement, but two visions of existence, one mechanistic, one holistic.
The war comes, and the quantum dream is conscripted into terrible service. The nucleus, understood now through quantum principles, becomes the key to unimaginable energy. Fission and fusion, once the abstractions of laboratory notebooks, leap into fire. The quantum description of probability becomes the logic of annihilation. The equations of Dirac and Fermi guide the construction of the atomic bomb. In Los Alamos, physicists trained in the language of uncertainty find themselves wrestling with moral certainties instead. When the desert blooms into nuclear light, the quantum world's deepest irony unfolds. The mathematics born to explain the smallest scales has changed the fate of the largest. Bohr visits the United States during the project, counseling caution, whispering of open-world diplomacy. His words, like photons, scatter, absorbed by some, reflected by others. The bomb drops. Hiroshima and Nagasaki vanish in quantum fire. After the war, the surviving physicists return to the quieter laboratories, chastened but unbroken. The same principles that split the atom now drive peaceful discovery. Particle accelerators rise like cathedrals of steel. hurling protons against targets to glimpse the architecture of matter. Every collision is a question posed to nature, and every spray of fragments an answer written in subatomic hieroglyphs. Out of these experiments emerges a growing zoo of particles: pions, kaons, muons, neutrinos, each one a note in the symphony of the quantum world. The old simplicity of proton, neutron, and electron crumbles under the avalanche of discovery. Physicists begin to suspect that even these so-called fundamental particles are not ultimate. In the 1960s, quarks are proposed, tiny constituents bound by the strong force, forever confined, never observed in isolation. They carry whimsical names: up, down, strange, charm, top, bottom, conceived half in jest, half in awe. The quantum universe, it turns out, has a sense of humor. Quantum field theory expands to embrace these new actors. The electroweak theory of Glashow, Weinberg, and Salam unites electromagnetism and the weak nuclear force into a single framework, predicting new particles, the W and Z bosons. Their discovery in 1983 crowns a generation's labor. Quantum chromodynamics, describing the strong interaction that binds quarks into protons and neutrons, emerges as the third pillar. Together, they form the Standard Model, a cathedral of mathematics that describes with staggering precision every known particle and force except gravity. Within its lattice of symmetries lies the Higgs field, a subtle sea whose excitation, the Higgs boson, gives mass to matter. In 2012, when the detectors at CERN finally register its signature, half a century after its prediction, the physicists' applause echoes through time. Planck's reluctant quanta have blossomed into an empire of phenomena. Yet even as the Standard Model triumphs, the mystery deepens. For the quantum world is not just a smaller version of ours, it is a different reality altogether. Time and causality themselves waver under its gaze. Virtual particles flit in and out of existence, borrowing energy from the vacuum, in accordance with Heisenberg's uncertainty principle. The emptiness of space is not truly empty, but foaming with fluctuations. Gravity, so smooth and geometric in Einstein's general relativity, refuses to fit within this jittering quantum tapestry. Attempts to merge the two, quantum gravity, string theory, loop quantum gravity, struggle across decades, weaving new mathematical fabrics whose patterns shimmer just beyond experimental reach. In these theories, space-time itself may be quantized, composed of discrete units of geometry, or vibrating strings whose harmonics define the particles we know. The universe, in this vision, is music made of probability.
Meanwhile, the philosophical ghosts of the early debates return in new guises. In 1964, John Bell, a quiet Irish physicist, formulates his famous inequalities, showing that no theory of local hidden variables can reproduce all the predictions of quantum mechanics. When experiments, decades later,
most notably those by Alain Aspect in the 1980s, confirm violations of Bell's inequalities. The verdict is in. The quantum world is indeed non-local. Entanglement is not a trick or a loophole. It is a feature of reality. Two particles, once intertwined, remain connected across any distance, their fates correlated beyond the reach of classical cause. Einstein's spooky action is not an illusion, it is the fabric of the cosmos. From this revelation arises a new frontier, quantum information. If entanglement is real, it can be used. The bits of classical computation, zeros and ones, yield to qubits, capable of existing in superpositions of both states at once. Quantum computers, still embryonic but promising, exploit this multiplicity to perform calculations that would cripple ordinary machines. The mathematics of Hilbert spaces and unitary transformations becomes the machinery of future technology. Quantum cryptography, using the fragility of entanglement, promises unbreakable communication. A single act of observation destroys an eavesdropper's attempt to intercept. The same uncertainty that once frustrated measurement now safeguards secrecy. Physics, having shaken philosophy, now begins to remake information itself. To trace how humanity arrived here, one must not only follow the equations, but the people who dared to write them. Max Born, who coined the probabilistic interpretation of the wave function, fled Nazi Germany and found refuge in Britain. His idea that the square of the wave function gives the probability of finding a particle cemented the statistical nature of reality. Wolfgang Pauli, brilliant and mercurial, contributed the exclusion principle, explaining why electrons occupy distinct states, why matter has structure, why stars shine. His sharp tongue and deeper melancholy colored every conversation. Heisenberg called him the conscience of physics. Louis de Broglie, a French aristocrat with the soul of a poet, proposed that not only light, but all matter has wave properties, linking the microcosm to the macrocosm in rhythmic unity. His hypothesis, proven soon after by electron diffraction, made the world itself vibrate with potential. Consider also the instruments that made the invisible visible. The cloud chamber of Charles Wilson, where charged particles left ephemeral trails of condensation like ghosts on glass. The bubble chambers of later decades, capturing collisions in liquid hydrogen, each photograph a frozen fragment of quantum choreography. The scanning tunneling microscope, born in the 1980s, that allows humans to see and even move individual atoms. The experimenter's hand, guided by quantum tunneling itself, arranges matter atom by atom, turning Heisenberg's uncertainty into artistry. These tools are not mere extensions of sight. They are collaborations with the quantum world, translations of probability into pattern. Beyond the laboratories, quantum thought infiltrates culture. Philosophers wrestle with its implications. If observation creates reality, what of free will? What of consciousness? Some see in quantum mechanics a refuge for the human spirit in a mechanized age. Others see it as the final dethronement of human centrality. The debates rage in salons and seminar rooms alike. Schrödinger himself, long after his cat became a symbol of paradox, turns toward Eastern philosophy, seeking in Vedanta parallels to quantum unity. The Western mind, fractured by certainty, begins to glimpse the ancient intuition of interconnectedness anew. In the cold mathematics of Hilbert spaces, some sense a quiet echo of mysticism. But within the physics community, the discipline remains rigorous, unsentimental, tethered to experiment. Each generation rediscovers the tension between understanding and utility. Feynman himself warned that no one truly understands quantum mechanics, yet every engineer uses it daily. The semiconductors that drive computers, the lasers that read disks and scan barcodes, the atomic clocks that define time, all hum with the precision of quantum principles. Global civilization, in its digital pulse, beats to the rhythm of Planck's constant. And yet, the fundamental questions remain untouched, shimmering at the horizon like mirages. What collapses the wave function? Does consciousness play a role? Is the universe deterministic beneath its quantum veil, or is chance woven into its essence? In the late 20th century, new experiments push the boundaries of strangeness. In quantum optics laboratories, photons are entangled, split, recombined, delayed, and measured with exquisite control. Delayed choice experiments, inspired by Wheeler, show that decisions made after a photon passes through a slit can determine whether it behaved as a wave or a particle, as if causality itself were elastic. Quantum erasers seem to erase which path information retroactively, restoring interference patterns that had vanished. Time, that sacred axis of cause and effect, bends before the observer's question. Reality, it seems, waits to be asked before deciding what it is. At the same time, the vastness of the cosmos begins to reveal its quantum roots. The cosmic microwave background, that faint afterglow of the Big Bang, bears the fingerprints of quantum fluctuations stretched to cosmic scales during inflation. The galaxies themselves may be the fossils of quantum noise, amplified by gravity into the architecture of the universe. In the equations of cosmology, the smallest and the largest intertwine, the Planck scale whispering to the scale of billions of light years. Quantum mechanics, once confined to atoms, now writes the story of creation. Still, the problem of measurement refuses to die. The many worlds interpretation, proposed by Hugh Everett in 1957, offers a radical escape. The wave function never collapses. Instead, every possible outcome of every quantum event splits the universe into parallel branches. Each observation is merely a bifurcation in an infinite multiverse, each version of the observer following its own path. To some, it is elegant. to others unbearable. Schrödinger's cat in this picture is both alive and dead, but in separate universes, each as real as the other. The price of determinism is infinity.
Quantum decoherence, a more recent insight, reframes the question. It suggests that interaction with the environment, air molecules, photons, even distant fields, destroys superpositions, making the quantum world appear classical. The collapse, then, is not mystical, but practical. The world's interconnectedness dissolves quantum ambiguity faster than we can perceive it. Our macroscopic certainty is an illusion of scale, not a law. The boundary between quantum and classical, once thought absolute, becomes a gradient of complexity. And now, in the 21st century, the story continues in laboratories glowing with laser light and cryogenic stillness. Trapped ions, superconducting qubits, photonic circuits, each is a theater where the principles born in Planck's blackbody now dance in programmable form. Quantum teleportation, once a dream, is demonstrated across kilometers, transferring the state of one particle to another without moving the particle. Entanglement links laboratories across continents, and satellites beam quantum keys through the upper atmosphere. The world is knitting a new web of communication built not on bits of certainty, but on qubits of possibility. Theoretical physics, too, presses forward into realms where imagination strains. Quantum field theory meets thermodynamics in the study of black holes, where the event horizon becomes a stage for paradox. Hawking radiation, predicted in the 1970s, shows that black holes can evaporate through quantum effects, slowly leaking energy until they vanish. But if information is lost in this process, quantum mechanics itself is violated. The information paradox drives decades of debate, from Hawking to Susskind to Maldacena, leading to the holographic principle, the audacious idea that the universe is a projection, its three-dimensional content encoded on two-dimensional boundaries. In this view, the cosmos itself is a quantum information processor, space and time emerging from entanglement patterns. What began as Planck's desperate calculation has become a metaphysics of existence. As the century turns again, the quantum world ceases to be an exclusive sanctuary for physicists and mathematicians. It begins to seep into every domain of human curiosity. Biologists, once content with chemistry and Darwin, now look through the lens of the quantum to explain the improbable precision of life. Photosynthesis, that ancient alchemy of sunlight and leaf, appears to exploit quantum coherence, the delicate alignment of wave functions to channel energy efficiently across molecular pathways. In migratory birds, the faint geomagnetic whispers of Earth seem to interact with quantum entanglement inside specialized proteins, granting the creatures an internal compass tuned by the probabilistic hum of the universe. Even the human sense of smell, long considered a simple matter of molecular shape, may instead depend on quantum tunneling of electrons through scent molecules, converting invisible probabilities into the poetry of perception. Life, it seems, has been whispering in quantum for billions of years, long before Planck gave the phenomenon a name.
Meanwhile, engineers push the boundaries of control. In laboratories cooled to near absolute zero, they coax single atoms into traps of light, manipulate them with laser pulses, measure them without destroying them. Quantum coherence, once fleeting, becomes manageable. Entanglement, once a philosophical oddity, becomes a resource. Quantum computing architectures arise like competing kingdoms, superconducting circuits in one, trapped ions in another, photonic chips in a third. Each seeks to master decoherence, to hold the fragile wave function stable long enough to perform a computation that no classical machine could dream of. Algorithms written by theorists decades before, Grover's search, Shor's factorization, wait like incantations for a machine powerful enough to give them voice. The prospect of quantum supremacy, a calculation demonstrably beyond the reach of any traditional computer, becomes both milestone and myth. In 2019, Google announces that its processor, Sycamore, has achieved it, completing in minutes a task that would take millennia for classical machines. The claim sparks debate, but the direction is undeniable. The future of computation is entangled. Outside the laboratories, the language of quantum begins to infiltrate metaphor itself. Economists speak of quantum decision theory. Artists paint interference patterns across canvases. Philosophers reinterpret free will through the lens of superposition. Some of it is nonsense, some inspired, but all testify to the same hunger, to grasp what the quantum revolution really means for human existence. For more than a century, it has defied intuition, and yet intuition reshapes itself around it, generation by generation. A child born today will grow up in a world where quantum technology is as ordinary as electricity once was, and where the word measurement carries echoes of cosmic participation. Still, among physicists, humility prevails. The deeper they probe, the less solid the foundations appear. Quantum field theory, for all its triumphs, predicts infinities that even renormalization cannot tame beyond certain scales. At the Planck length, 10 to the minus 35 meters, space-time itself is expected to foam and fluctuate, destroying the very background on which the equations are written. Gravity, relentlessly geometric, resists quantization. String theory, for all its mathematical elegance, expands into a landscape of possibilities so vast that prediction dissolves into choice. Loop quantum gravity offers a rival vision, quantizing space into spin networks and discrete volumes, yet its experimental signatures remain elusive.
The unification of quantum mechanics and general relativity, the dream of Einstein's final decades, remains tantalizingly incomplete. The universe keeps a secret, and perhaps that secrecy is its truest law. Meanwhile, the experimentalists continue their long game. The Large Hadron Collider circles beneath the Franco-Swiss border, smashing protons at energies once confined to the earliest instance after the Big Bang. Each collision is a small resurrection of creation's dawn, a microcosm of chaos distilled into data. Detectors, layered like onion skins of technology, capture the fleeting traces of quarks, gluons, leptons, and bosons, turning ephemeral flashes into terabytes of insight. The Higgs boson, once found, raises as many questions as it answers. Why is its mass what it is? Why does the vacuum not collapse? Is there symmetry beyond the standard model? Supersymmetry, perhaps, where every particle has a hidden twin? None yet appear. Dark matter, the unseen scaffold of galaxies, remains silent. Dark energy, that mysterious force accelerating cosmic expansion, defies even the vocabulary of quantum theory. The more physics learns, the larger its ignorance grows, a fractal boundary forever retreating. Yet in uncertainty, beauty persists. The mathematical structures underlying quantum theory, Hilbert spaces, Lie groups, gauge symmetries, possess an elegance that borders on art. Feynman once said that nature uses only the longest threads to weave her patterns, so each piece of her fabric touches the rest. In quantum theory, that statement becomes literal. Everything is entangled with everything else. The separations we perceive between observer and observed, cause and effect, matter and energy, are conveniences, not absolutes. The physicist's blackboard, scrawled with symbols, becomes a kind of musical score, each equation a melody of existence. Consider for a moment the constants that define this strange symphony. Planck's constant, h, small but omnipresent, measures the granularity of action in the universe. The speed of light, c, links energy and mass, space and time. The gravitational constant, g, whispers of the curvature of space-time. Together, they define the Planck units, the natural scales at which quantum gravity must emerge. At those scales, a grain of space is as significant as an atom was to Democritus. But unlike atoms, these grains of space-time cannot be separated or seen. They are pure relation, pure potentiality. The search for their nature is the frontier of the next century. In quieter corners of the world, philosophers of science revisit the early paradoxes with new tools. They examine the language of complementarity, the ontology of the wave function, the role of information as the new foundation of reality. Some propose that information, not matter or energy, is the true substrate of the universe, that what exists is the computation of existence itself. The quantum bit, they argue, is the new atom of being. Each measurement is a yes or no, a 1 or 0, a question asked and answered by the cosmos. The world becomes a conversation between probability and actuality, a ceaseless dialogue that writes itself into reality. In this frame, the observer regains a curious centrality, not the human ego, but the act of interaction, the fundamental process by which systems exchange information and collapse possibilities into events. Every photon scattered, every atom touched, every neuron firing is an instance of this universal grammar. Consciousness may be a higher-order manifestation of quantum information processing, a self-reflective pattern of entanglement that calls itself I. Though speculative, the idea seduces that the mind is the quantum made self-aware. Schrödinger himself, in his later writings, toyed with such unity, suggesting that there is no multiplicity of consciousness, but one mind reflected in many mirrors. Physics, philosophy, and mysticism, after centuries of separation, find themselves neighbors again. And yet the discipline remains anchored in experiment. Quantum communication satellites orbit Earth, exchanging entangled photons across thousands of kilometers, proving that non-locality transcends the boundaries of atmosphere and distance. The dream of a quantum internet begins to coalesce. Networks where information exists in superposition, transmitted securely through the fragile thread of entanglement.
Meanwhile, education struggles to translate these marvels to common understanding. How do you teach a child that an electron does not have a position until measured, or that the vacuum teems with invisible activity? Popularizers turn to metaphor, dice, cats, waves, and particles. But each metaphor eventually betrays its inadequacy. Quantum physics resists storytelling because it is not a story, but a framework of relationships. Still, storytellers persist, crafting analogies that bring awe where comprehension falters. Perhaps awe is the truest understanding, the recognition that reality is more subtle than the mind that perceives it. In literature and art, the quantum revolution finds echoes in narrative form. Modern novels fractured timelines, juxtapose perspectives, and embrace ambiguity, mirroring superposition in human experience. Cinema experiments with branching realities, parallel outcomes, and tangled destinies. The very structure of storytelling evolves to accommodate uncertainty, just as physics did. The deterministic clockwork of 19th century fiction yields to the probabilistic weave of modern thought. The quantum has changed not only how we see the world, but how we imagine it. And still, beneath the poetry and progress, the core mystery endures unchanged since Planck's first calculation. Why should the universe be quantized at all? Why should energy, momentum, and charge come in discrete packets? Why does the act of observation hold such power? Some theorists suspect that quantization is the inevitable consequence of information stability, that continuous systems could never sustain memory or causation, that the digital is built into the fabric of being. Others propose that what we call quantization is merely a reflection of our limited perspective, that a deeper theory might reveal continuity once again. Between these poles lies the fertile field of speculation, where science and philosophy cohabit. In this landscape, figures like Roger Penrose wander with bold conjectures, linking consciousness to quantum gravity, proposing that microtubules in neurons sustain quantum coherence long enough to influence thought. Critics scoff, yet experiments continue, small and meticulous, probing whether the mind itself might host quantum phenomena. Meanwhile, cosmologists turn the same questions outward, exploring whether the entire universe, in its earliest moments, was a quantum fluctuation emerging from nothingness, its total energy balanced at zero, its existence a statistical inevitability. The line between physics and metaphysics grows thin.
And so, quantum physics, born of a furnace's glow, expands to embrace the entire cosmos. It is both the hum of electrons in a superconductor and the whisper of creation itself. It is the grammar of matter, the poetry of light, the secret rhythm by which the universe dances with itself. From Planck's hesitant quantization to the holographic universe, from Einstein's defiance to the algorithms of quantum code, it traces a single continuous arc, a history not of certainty, but of ever-deepening wonder. In the second decade of the 21st century, quantum mechanics becomes not only the foundation of technology, but a mirror of civilization's psyche. The same uncertainty that rules electrons seems to permeate politics, culture, even identity. Humanity, navigating its own entangled crises, begins to recognize in the equations of the microcosm an allegory for its own contradictions, multiplicity within unity, potential collapsing into actuality through the act of choice. Physicists smile at the metaphor, yet feel its resonance. For them, the equations are literal, but they know how deeply those equations have reshaped human thought. Once, knowledge meant certainty. Now, knowledge means probability. The transition is not only intellectual, it is existential. In the laboratories of Delft, Vienna, and Shanghai, researchers achieve feats once considered science fiction. Loophole-free tests of Bell's inequalities, entangling macroscopic systems, teleporting quantum states across metropolitan distances. The fragile link between theory and experiment, stretched for a century, grows taut and brilliant. Quantum mechanics, once a strange newcomer, now commands the precision of engineering. Yet even as it becomes practical, it never loses its mystery. Each successful experiment feels like the universe nodding in quiet approval, saying, "You have understood enough to use me, but not enough to explain me. In metrology, the science of measurement itself, quantum physics redefines reality. The kilogram, once a metal cylinder in a vault near Paris, becomes a quantity defined by Planck's constant. The second, the meter, the ampere, all now anchored to quantum phenomena. Atomic transitions, photon frequencies, electron charges. Human standards yield to cosmic constants. The instruments that measure the universe are calibrated by the same universe they describe. In this recursive act, science achieves a new purity. Every clock, every GPS satellite, every data network now ticks to the rhythm of quantum coherence. Civilization synchronizes itself to the heartbeat of the atom. At the same time, a subtler revolution unfolds in theory. The intersection of quantum mechanics and information theory begins to reframe physics itself as a study of computation. Physicists like Wheeler and Lloyd propose that the universe is not made of matter, but of information, that every particle interaction is a logic gate, every field a processing channel. It from bit, Wheeler declares. Every entity of physics derives from binary yes-no questions answered by observation. Thus, quantum mechanics becomes not merely the science of the small, but the ontology of inquiry. The universe is not a machine, but a dialogue.
In this dialogue, entropy plays the role of storyteller. The second law of thermodynamics, once a statement about heat, becomes a statement about information loss. Entropy increases because information disperses. Order dissolves into probability. Black holes, those cosmic abysses once thought to destroy everything, turn out to be archives of information. Their event horizons encode the details of everything they consume, measured in bits per Planck area. From this strange realization emerges a principle as profound as any in science. The amount of information a region of space can contain is proportional not to its volume, but to its surface area. Thus, the holographic principle. Reality is a projection from a deeper informational layer. Space-time, energy, matter, all may be emergent phenomena, the way temperature emerges from molecular motion. The universe, in this view, is a quantum computer calculating itself into being. Meanwhile, experimenters explore the boundaries of coherence in ever larger systems. Superconducting circuits sustain superpositions of current flowing clockwise and counterclockwise simultaneously. Nanomechanical resonators vibrate in two phases at once. Molecules of thousands of atoms pass through double slits, still producing interference patterns, as if mocking the idea that quantum effects are confined to the small. The line between quantum and classical dissolves, not because the quantum retreats, but because our control extends. The cat in Schrödinger's box grows larger each year, not metaphorically, but literally, as experiments push superposition toward the macroscopic. What once seemed philosophy becomes engineering. And yet, with every success, a question returns like a refrain. What is a wave function? Is it real, a physical field in configuration space, or is it merely epistemic, a mathematical device encoding knowledge? The realist and instrumentalist schools trade papers and counter-arguments. Some propose Scientology, asserting that the wave function is as real as any field. Others champion QBism, interpreting it as a statement of personal belief updated by measurement. The debate is no longer about equations, they are secure, but about the meaning of those equations, the territory they describe. Quantum mechanics has survived a century of assault without ever revealing its metaphysical core. It is as if the theory itself were a quantum object, measurable, predictive, and yet fundamentally indeterminate. Beyond Earth, quantum thought travels to space. The Chinese satellite Messius distributes entangled photons between ground stations thousands of kilometers apart, testing quantum communication in the thin, unyielding vacuum above the world. Future missions aim to test gravitational decoherence, to see whether entanglement survives across the curvature of space-time. Einstein's general relativity and quantum mechanics, once estranged, meet again in the upper atmosphere, their principles intertwined in orbit. The ancient question, does gravity itself have quantum nature, edges closer to experimental resolution.
In cosmology, too, the quantum continues to whisper. The inflationary model, explaining the uniformity of the universe, relies on quantum fluctuations magnified to cosmic scale. Each galaxy cluster, each star, each planet is an echo of quantum randomness from the universe's first instant. In the cosmic background radiation, measured by satellites with breathtaking precision, scientists see the fingerprint of wave functions stretched by expansion, frozen into space itself. The night sky, in this sense, is the fossilized record of quantum noise. The randomness that once puzzled Planck now shapes the pattern of galaxies. The reach of quantum physics extends even into philosophy of time. The Wheeler-DeWitt equation, a cornerstone of quantum cosmology, describes the entire universe without reference to time. Time, according to this equation, is not fundamental. It emerges from correlations between quantum states. If this is true, the universe is timeless at its root, a static superposition of possibilities. What we experience as the flow of time is the unfolding of entanglement, a pattern of correlations within a larger whole. Past and future, like wave and particle, are complementary aspects of a single reality beyond sequence. The arrow of time, driven by entropy,
becomes an emergent illusion, a narrative woven by consciousness as it moves through the probability landscape. Meanwhile, new experiments probe quantum mechanics in the biological domain. In Cambridge and Vienna, researchers study photosynthetic complexes cooled to near absolute zero, watching excitons, quantum particles of energy, move through them with coherence lasting hundreds of femtoseconds. In those fleeting intervals, the system explores multiple paths simultaneously, selecting the most efficient route to the reaction center. Life, evolved under the sun's light, appears to have harnessed quantum optimization long before humans named it. The boundary between physics and biology erodes. The old divisions of knowledge crumble as the same mathematics describes the chloroplast and the circuit board, the neuron and the photon. And still, the intellectual descendants of Bohr and Einstein argue across time. New generations re-examine their correspondence, finding in their disagreements the seeds of creativity. Bohr's complementarity and Einstein's realism, once opposed, now appear as two sides of a dialectic that drives science forward. Without Bohr's insistence on the limits of knowledge, there would be no humility. Without Einstein's refusal to surrender determinism, there would be no search for deeper theory. The argument itself becomes part of the quantum heritage, a reminder that understanding grows in tension, not agreement. The cultural image of the physicist changes too. No longer the isolated sage of the early 20th century, the modern quantum scientist works in teams of hundreds, united by shared instruments and data streams. Their blackboards are replaced by simulations, their calculations by quantum algorithms running on prototype machines. The romance of solitary discovery gives way to the orchestration of collaboration. Yet the sense of wonder remains the same. Each time a detector clicks, each time a probability collapses into an event, the same thrill runs through the human mind. We have glimpsed the machinery of existence at work.
From the quiet corridors of universities to the roaring data centers of global technology firms, quantum ideas begin to rewrite the economy itself. Quantum encryption guards communications. Quantum sensing detects submarines and earthquakes. Quantum annealers optimize logistics and financial systems. The quantum revolution, like electricity in the 19th century, becomes invisible through ubiquity. The future historian will note that the 21st century's infrastructure runs not on copper and steel, but on coherence and entanglement. And yet, beneath the progress, the philosophical question persists, unchanged and undiminished. What is reality? After all the mathematics, all the instruments,
all the proofs and applications, the quantum still whispers that reality is not what it seems. Every observation is both discovery and creation. Every measurement, both question and answer. Perhaps that is the ultimate lesson of the quantum century. Not that nature is strange, but that strangeness is natural. That uncertainty is not ignorance, but structure. In the dim archives of history, one might imagine Planck looking up from his equations, Einstein lifting his eyes from his desk, Bohr leaning against a window in Copenhagen, Heisenberg sketching matrices on Helgoland, Schrödinger dreaming of waves in Zurich, Dirac carving simplicity from symmetry. None of them could have foreseen satellites entangling photons across continents, or machines performing calculations in superposition, or the measurement of a Higgs boson's mass with 12 decimal places of precision. And yet each of them contributed a fragment to the same unfolding symphony, each note reverberating across a century. Their debates, their doubts, their humility built the scaffolding on which the modern world stands. The story of quantum physics is not finished. It may never finish. Like the wave function itself, it evolves endlessly, branching into new possibilities with each experiment, each generation, each idea. It has carried humanity from the glow of a furnace to the edge of the multiverse, from the trembling of electrons to the birth of space and time. It has rewritten the definition of reality and left us standing in wonder at the sheer audacity of existence. And somewhere, in the silence between probabilities, in the infinitesimal tremor of a photon, or the hesitant orbit of an electron, the universe continues to whisper its secret, slowly, inexhaustibly, quantumly.